Okay, we want to model projectile motion with parametric equations. Projectile motion is when something is launched, thrown, shot, whatever, on the surface or near the surface of the Earth. And essentially you have your initial velocity. This shows the vector here with v naught, meaning the velocity when it is launched. And you will have an angle theta, whatever angle, if it's shot out of a cannon, how it's pointing, or an arrow or whatever. And so to model this, we've got a couple things going on. We want to see how much of this is in the horizontal or x direction and how much of this is in the vertical or y direction. And then we will also have gravity coming into play as it tries to, instead of launching and staying going straight up, gravity is going to be pulling on it. So essentially it will have a parabolic shape and it'll curve around following this parabola that you see and then come back and land on the ground. So we're interested in, first of all, finding the component of the velocity acting in the horizontal direction. So we're going to take this vector, we're going to draw down to make a right triangle. We're going to figure out the x or horizontal component and the y or vertical component. So connecting the x with the theta and the v naught, that would be cosine theta equals adjacent over hypotenuse. So acting in the x direction would be v naught cosine theta. So if you gave me an initial velocity, I would put that in front of the cosine and then gave me the angle that we're launching from, and I put that in the cosine. All right, so if we want to know the component acting in the vertical direction, we will do the same thing but involving y. So that would be sine theta equal y over v naught. So the component in the vertical direction would be y equals v naught sine theta. Now this models how this is moving both horizontally and vertically, but it's a function of time. For the time that goes by, it moves by this much. And so when we write these equations, x is going to be a function of time. So this v naught cosine theta multiplied by t, and the vertical is going to be this v naught sine theta, but you've also got gravity pulling on it, and if you have gravity acting near the surface of the Earth, you need a term in there, negative 1/2 the gravity constant t squared, and the gravity constant is 32 feet per second squared. It's what the gravity is pulling down on it if your units are feet in seconds, or 9.8 if they're meters in seconds. And so we need to have that term on there to take gravity into account. So if we were modeling this when we've got gravity into account, we are going to put the gravity term first. Usually you do that because it's the t squared term. So it would be negative 1/2. We would put in 32 and then t squared. And it's negative because the gravity is pulling it down, but from launching it's wanting to go up by v naught sine of t. So this is like a number that will be in front of the t. Now if you were not at ground level, maybe you're on a launching platform or you were up on a cliff or something, you could have a term for the initial height. And so when we're trying to get these equations, our x of t is always going to be this because that's going to be how it moves horizontally. But our y, we've got gravity pulling it down, and we could have an initial height. And so if you were modeling, say, a baseball that was hit by a bat, you wouldn't be at ground level. You'd be up, a kind of level with where the batter would swing. So you would add that term on the end. So we combine the negative 1/2 and the 32. That's going to be negative 16 t squared plus v naught sine, oh, I left off the theta. That's what looked funny. Sine theta t, and then plus y naught, and y naught means the initial height, so the level of the bat or up on the cliff or whatever that might be. So our two equations, the one I circled, x of t for projectile motion would be what I've got here, and y of t would be this, and you may not have the plus y naught, it might be 0. If you're at ground level, you just have a 0 there, so that term isn't there. Okay, so let's see how to use these equations. We've got a kind of a word problem now. A center field fence in a ballpark is 10 feet high and 400 feet from home plate. A baseball is hit at a point 3 feet above the ground and leaves the bat at a speed of 150 feet per second at an angle of 15 degrees. Write the parametric equations for the baseball's path, and then we'll graph the path of the ball, and we'll see if this was a home run, if it got hit over the fence. And to get hit over the fence, when the horizontal distance is 400, the height needs to be at least 10 to clear the fence. It could be higher, but at least 10 to go over the fence. All right, so let's write the parametric equations. So first we have x of t, and that equals v naught, the initial velocity, was 150 feet per second. So that's going to be 150 cosine, the angle was a 15-degree angle, so cosine of 15 degrees t. So that would model what it's doing in the x direction, and we're just going to use the calculator, and we're just going to round to the nearest whole number. So we could have figured out 15 degrees of cosine exactly with a half angle formula, but we're interested in knowing if it goes over the fence, so we need numbers for this. So we're going to do 150, make sure we're in degrees, cosine of 15, and it looks like that is 144.88 something. We're going to round it then. So this is going to be 145 t. So that's going to be our horizontal position at time t. And then to figure out our vertical position, we have the negative 16 t squared on the front of it because gravity is pulling it down, plus we have the 150 sine of 15 degrees, and then we need to put a t on that, and then on the end we have plus 3 because the bat where it was hit was up 3 feet. Now let's go ahead and work this. We're going to round it to the nearest whole number again. So we have y of t equal negative 16 t squared. Putting that 150 sine 15 in the calculator and rounding to the nearest whole number would be plus 39 t and then plus 3. So we have our first part of that, which is this will model what the ball does given a time t. We see at 0, the x is 0. We're starting, that's where we measure from. It hasn't moved horizontally yet. And putting 0 in the y, we're up 3 feet where it's hitting the bat. All right, so if we wanted to figure out a graph of this, we can start there. Let me slide this up a little bit. Okay, so I would start here at 0, it's up 3. Okay, and we need to model what's going on here, so let's pick some t values. So I'm going to just make a little chart here and pick some t values and figure out the x and y, and I started with 0 and the x was 0 and the y was 3. Let's do 1 second and 1.5 seconds and 2 seconds and just kind of see what's going on here. And then we could actually, what we'd want to also do is figure out how many seconds before it hits the ground, because the model's not valid after it hits the ground. So let's do that first. So I'll know, do I really go to 2 or do I need to go past 2, and how high do I need to go? So when it hits the ground is when the y value equals 0. So if we figured out when this equals 0, we will know when it hits the ground. Well, this is a quadratic equation that doesn't factor, so I can figure out when it hits the ground if I do negative b, that's 39, plus or minus the square root of b squared, that's 39 squared, minus 4 times a, which is negative 16, times c, which is 3, all over 2a, which was negative 16. That's just a quadratic formula. And we can work it once with the plus and once with the minus, and you could put that in your calculator. Just make sure when you do that that you include all of this in the numerator, and there'd be parentheses for what's under the square root. And so when you put that in the calculator, I get 2 different answers. I get t, and I'm going to just go to a couple decimal places, negative 0.07, and I get 2.5. Now these are time in seconds. This one doesn't count because it's negative, and it's basically if you trace the parabola back through 0 and came down and saw where it hit the x-axis, it's over there with the negative x's. So that doesn't apply to our model because our model starts when it's at 3 feet hitting the bat. So at about 2.5, I rounded it, seconds is when it hits the ground. So I could put 2.5 in to see how far it went horizontally to see if it's going to clear the fence. So let's take our x of t and let's put in 2.5 and see what horizontal distance it moved to get to 2.5 seconds. So I've just got 2.5 times 145, and that's going to be 364. That's feet. Well, the fence was over there at 400, so it's not going to be a home run. It's going to land in front of the fence. And so I've answered one question, is it a home run? We're still supposed to graph the path of the ball. I can put another value on my chart here at 2.5. The x is about 364 and the y is 0 because it's back on the ground. So we'll put this over here at 364. It's back on the ground. Okay, so if we put 1 in, for x, we get 145. And if we put 1 in for y, we're rounding to the nearest, we get 26. Okay, if we put 1.5 in, we get 217 for the horizontal distance, and we get about 25.5 for the vertical distance. If we put 2 in, we get 290, and we get 17. So we could plot these points so that we could get a sketch of this parabola. I went ahead and actually plotted it in Desmos, and I wanted to show you that. So here it is in Desmos. And by the way, how do you plot parametric equations in Desmos? You make them as an ordered pair. So I made a parenthesis and I put the x of t, which is 145t, and then a comma, and then I put the y of t, which is negative 16t squared plus 39t plus 3. And then you have to tell it what you want the t to go between. And so it starts at 0, and I wanted it to complete till it hit the ground. So I put 2.52 to see what happened here. I kind of adjusted it till I saw it, and that's a little ways past the ground, but 2.5 was when it hit the ground. So we can see the shape of this thing nicely. And if we wanted to figure out where that vertex is, the maximum is about when the x is 175, so we can put the x equal to 175, divide that by the 145 to see what time. And so about 1.2 seconds it will be at its maximum. And it looks like its maximum value is about a little under 27. So if I put 1.2 in the y, I get 26.7. So at 1.2 seconds, it's at the vertex there of about 26.7 feet. So going back to the activity then, so right here in the middle, okay, that was when the t was about 1.2 seconds. And this was the highest that it gets. So this was the point 1.2 and 26.7. So it follows this parabolic shape, comes back down like this, and it does not clear the fence.